We've already seen how to do an acid-base titration. Now let's look at a redox titration. So let's say we have a solution containing iron 2+ cations. So we don't know the concentration of the iron 2+ cations, but we can figure out the concentration by doing a redox titration. Let's say we have 10 milliliters of our solution, and let's say it's an acidic solution. So you could have some sulfuric acid in there. And so in solution we have iron 2+ cations and a source of protons from our acid. To our iron 2+ solution, we're going to add some potassium permanganate. So in here, we're going to have some potassium permanganate, KMnO4. And let's say the concentration of our potassium permanganate is 0.02 molar. So that's the concentration that we're starting with. And potassium permanganate is, of course, the source of permanganate anions, because this would be K plus and MnO4 minus. So down here we have a source of permanganate anions. And we're going to drip in the potassium permanganate solution. And when we do that, we're going to get a redox reaction. Right? So here is the balanced redox reaction. And if you're unsure about how to balance a redox reaction, make sure to watch the video on balancing redox reactions in acid. But let's look at some oxidation states really quickly so we can see that this is a redox reaction. For oxygen, it would be -2, and we have 4 oxygens, so -2 times 4 is -8. Our total has to add up to equal -1. So for manganese, we must have a +7, because +7 and -8 give us -1. So manganese has an oxidation state of +7. Right, over here for our products, we're going to make Mn2+. So manganese 2+ cation in solution, so the oxidation state is +2. So manganese is going from an oxidation state of +7 to +2. That's a decrease or a reduction in the oxidation state. Therefore, manganese is being reduced in our redox reaction. Let's look at iron 2+. So we have iron 2+ as one of our reactants here. So that means the oxidation state is +2. For our products, right, we're making iron 3+. So an oxidation state of +3. So iron is going from +2 to +3. That's an increase in the oxidation state. So iron 2+ is being oxidized in our redox reaction. So as we drip in our potassium permanganate, right, we're forming our products over here, right? So these ions are colorless in solution. So as the permanganate reacts, right, this purple color disappears, and we should have a colorless solution. Right? So let's say we've added a lot of our permanganate. Everything is colorless, but then we add one more drop and a light purple color persists. Right, so everything was clear, but then we add one drop of permanganate, and then we get this light purple color. This indicates the end point of the titration. And the reason why this is the end point is because our products are colorless. And so if we get some purple color, that must mean we have some unreacted, a tiny excess of unreacted permanganate ions in our solution. And so that means we've completely reacted all of the iron 2+ that we originally had present. And so we stop our titration at this point. We've reached the end point. All right, so we've used a certain volume of our potassium permanganate solution. So let's say we finished down here, and if we started approximately there, we can see that we've used a certain volume of our solution. Let's say it took 20 milliliters. So we use up 20 milliliters of our potassium permanganate solution to completely titrate our iron 2+. All right, our goal was to find the concentration of iron 2+. And if we're going to find the concentration of iron 2+, we could figure out how many moles of permanganate were necessary to completely react with our iron 2+. And we could figure out moles from molarity and volume. All right, so let's get some more room down here. We know that molarity is equal to moles over liters. The molarity of permanganate is 0.02. So we have 0.02 for the concentration of permanganate ions. Right, so moles is what we're solving for, and it took us 20 milliliters for our titration, which we move our decimal place 1, 2, 3, so we get 0.02 liters. All right, so solve for moles. 0.02 times 0.02 is equal to 0.0004. So we have 0.0004. And this is how many moles of permanganate were needed to completely react with all of the iron 2+ that we originally had in our solution. So it took 0.0004 moles of permanganate to completely react with our iron. All right, next we need to figure out how many moles of iron 2+ that we originally started with. And to do that, we need to use our balanced redox reaction. And we're going to look at the coefficients because the coefficients tell us mole ratios. So the coefficient in front of permanganate is a 1, right? And the coefficient in front of iron 2+ is a 5. So if we're doing a mole ratio of permanganate to iron 2+, permanganate would be a 1 and iron would be a 5. So we set up a proportion here. 1 over 5 is equal to, well, we need to keep permanganate in the numerator here. How many moles of permanganate were necessary to react with the iron 2+? That was 0.0004. So we have 0.0004 moles of permanganate. And so X would represent how many moles of iron 2+ we originally started with. So we could cross multiply here to solve for X. So 5 times 0.0004 is equal to 0.002. So X is equal to 0.002. And X represents the moles of iron 2+ that we originally had present. All right, so we're almost done because our goal was to find the concentration of iron 2+ cations. And now we have moles and we know the original volume, right, which was 10 milliliters. So to solve for the concentration of iron 2+, all right, we just take how many moles of iron 2+ we had, which is 0.002. So we have 0.002 moles of iron 2+. We started with a total volume of 10 milliliters, which is equal to 0.01 liters. So we have 0.01 liters here. And 0.002 divided by 0.01 is equal to 0.2. All right, so this is equal to 0.2 molar. And so that was the original concentration of iron 2+ ions in solution. So you could have used the MV is equal to MV equation and modified it because our ratio isn't 1-to-1 here. So that's another way to do it. But I prefer to actually sit down and do these calculations and think about exactly what's happening.